Yeah, I thank the organizers for giving me this opportunity to speak. Over the last 2 months, I have really enjoyed the program. I've learned a lot. Okay, the title of my talk is Discovering New Mathematical Structures with Machine Learning. So in this talk, I will show you how to use machine learning in mathematics research. Around 2017, machine learning experiments for mathematics began. Yesterday, Yang gave a nice overview. So it started with a group of string theorists. And the first pioneers were Yang Liu, Fabian Ruel, and Jim Halverson, and many other people. Okay. And in this morning, Ding Dong gave us a talk, and then, as he mentioned, in 2021, a Nature paper by Alex Davis and Jody Williamson appeared. And then the paper basically proposed a paradigm for math research using machine learning. And this new paradigm has led to some successes, several notable successes. So here is the summary of the paradigm. This is my version. So according to my understanding, let me try to summarize the paradigm. The first, we consider mathematical objects collectively to generate data sets. Instead of focusing on individual objects, we consider mathematical objects collectively. It's a shift of a perspective. Sometimes we just look at one curve, and after we look at another curve, etc. But here we consider those curves or whatever the objects may be, we consider them collectively, and then generate data sets. And because we have now data sets, we apply machine learning tools. Sometimes we get high accuracy, and then we get very clear signs of learning, successful learning. That's good. Other times, the machine learning results may be very poor, but that's okay. That gives us some information. And then we may modify the machine learning tools, or we change the data sets, and then we do experiments again, and we repeat the process. And after get all the results, I think this step is important. We have to interpret machine learning results to understand the mathematical objects better. Here, it is crucial for human mathematicians to play a role. Because we want to do mathematics research, we want to find out something new in mathematics. The human mathematicians should play a crucial role. And then it may take time and energy. And, but anyway, this step is important. And then this efforts may lead to discovery of new structures. For other times, actually, many times we find known structures, but from different perspectives, because we apply new tools from machine learning. So that's also valuable. And then we study those new structures and make conjectures, and eventually this may lead to new theorems. Okay, this is the paradigm. So in this talk, I will present 2 examples to show how this paradigm worked out. The first one will be the murmurations, and the second one is study of Kronecker coefficients. Okay, so first, murmurations. So this is a collaboration with Yang Liu, and then Thomas Oliver, Alexei Pasnyakov, and Drew Sutherland. Then here is a picture of a murmuration in Nature. Sure. Then another picture can be found on the poster of this workshop. And in mathematics, this murmuration phenomenon was first discovered in the data set of elliptic curves. So let me talk about elliptic curves. Of course, elliptic curves and then AP coefficients appeared many times during this workshop, but in order to be on the same page, let me go over those things quickly. So elliptic curve over Q can be defined by a cubic equation, the integer coefficients, and there is a huge database of elliptic curves. And then this curve has a label, it's 496.81 in the database. And the model Bayes theorem says the set of rational points on the curve makes a finitely generated abelian group. So it has the torsion part and the free part, and the rank of the free part is called the rank of the elliptic curve. So even though the elliptic curves and the rank of an elliptic curve has been studied for a long time, there are still many open questions. And then Noam Ilkis can tell us many hours about the rank of the elliptic curves. Yeah, there are, and then this is the quantity is difficult to compute. There is no general algorithm for all the cases. And then among the open questions, in particular, there is this Birch and Srinivasan-Dyer conjecture. This conjecture is directly related to the rank of. Okay, then because now we have new tools, I mean not new, but we have anyway some tools. Question in the context of this program, can we apply machine learning to classify elliptic curves according to their rank? So we can ask this question. Then immediately the next question is how to present an elliptic curve to a machine. That's a problem. I mean, that's the question we have to think about and answer. There may be several ways, but we remember that arithmetic objects have been studied through their L functions. So it may be a good idea to use their L functions. And so let me try to explain how we can use L functions. Again, the definitions that have appeared during this workshop and of course throughout the program, but let me go over the definition. So let E be an elliptic curve over Q, and for each prime P, we reduce the curve modulo P, and then count the number of rational points modulo P. And then let's call the number NP, denote the number by NP. And for each prime P, define AP to be the deviation of NP from P plus 1, that's AP. And these APs are basically the essential information. Of course, I mean, there are a lot more details, but in any case, these APs are used to define the L functions, L function of the elliptic curve. So for each prime P, we have a number, AP. So the idea was we fix the number of primes. Let's say the number is K. So first prime is 2, second prime is 3, and then can go all the way up to say 300, for example. Then the prime may be, I don't know, 1,000, something like that. Then we have a sequence of numbers, APs. Then on the elliptic curve E can be represented or presented by this sequence. Then we may consider this sequence as a picture of an elliptic curve. So picture is at the end of the day, picture is a sequence of numbers. So yeah, likewise, but even though the sequence is very short, relatively short in this case, if K is like a 300, for example. In any case, this is a picture of an elliptic curve. Now consider a set F consisting of elliptic curves, a family of elliptic curves. And then we can generate this data set. This can be done easily, or we can just download the data set from a database called the LMFDB. So we have a set of pictures, collection of pictures of elliptic curves. And then for pictures, we can do classification. So likewise, here, we may apply machine learning tools to classification problem, but let us have the rank of an elliptic curve as a label. And label can be from 0 to 1. It may go up, but the known record is now 29. So probably and then the number of elliptic curves are becoming smaller and smaller. So probably from 0 to 5 or 0 to 4 may be a reasonable range. But in any case, and then majority of elliptic curves have rank 0 or 1. So this is the machine learning problem, and it is a good problem. So we did this machine learning classification problem, and okay, here is more details. So we did it with, I did it with Yang and Tom, and later with Alexei. Then it's one of the experiments, one of the first experiments we did. We collected 16,000 elliptic curves of rank 0 and 16,000 elliptic curves of rank 1. And they had conductors ranging from 1 to 10,000. Here, the conductor is the measurement of how complicated a curve is. Then we chose k equal to 300. 300 is not a magic number. We just chose some reasonable number. And then we have this nice classification problem. And then this is a binary classification problem and supervised learning. The labels are known. Okay, and then we applied many machine learning algorithms, including neural network, but logistic regression was enough. So the logistic regression, and the result was, it was about 99%. So sometimes it was almost perfect. It was surprisingly high. And here are more details. So if we choose 300 APs, then the precision is 99%. If we reduce the number of primes to 100, then precision is now 97%, 97.7%. It's still very high. It's slightly smaller. And then we did also this experiment of classifying elliptic curves with the ranks 0, 1, or 2. It's not binary classification anymore. And then also this is not binary, but the others are binary classification. Anyway, we did some experiments. And yeah, all the time we got very high accuracy, and in particular, the distinguish rank 1 curves from rank 2 curves was the easiest. Okay, so we got these results, and then then we thought that machine learning is awesome. Yeah, it worked, and then it was fantastic. But we wanted to see what's going on. So we did more. So we did a PCA. So we applied basically the basic machine learning tools, PCA. Then here is the picture. So blue represents rank 0 curves in principal direction. It's the first principal direction and second principal direction. And red dots represent elliptic curves of rank 1. So you can see some clear separation. It's not really perfect, but anyway, it's separation. And if we consider rank 0, 1, and 2. So now green clusters are from rank 2 curves. And we got this picture. Again, the first principal direction separates these clusters. And then rank 2 curves are, this cluster is clearly separated from the other clusters. We see that by rank 2 case for the easy. And then this was the picture of the weights or the coordinates, basically coordinates of the principal direction. So each x-axis is prime count from the first prime to 3, etc., and then 300th prime. Then these are the coordinates of the first principal direction, loadings, or it can be called. So anyway, so it is it. And what do you think about it? So it tells us, in some sense, the importance of primes. And then naturally, the importance may decrease constantly because why is that? In any case, we don't. Yeah, there may be some rigorous explanations, but intuitively. But something should be like constantly changing. But of course, it is constantly changing. But obviously, there is oscillation. And there was interesting. So all these machine learning experiments eventually led to the discovery of murmuration. Your point is, we did all kinds of machine learning experiments, including PCA and then supervised learning classification, and we could find out murmuration. So after all, while we are doing these machine learning experiments, I asked Alexei Pasnyakov. At the time, he was undergraduate sophomore. I asked him to analyze the machine learning results, and one of the first things he did was to take the average of APs, which is a natural thing to do. So more precisely, fix a prime P, then take the average of AP over a set of elliptic curves for each rank. So rank 0 separately, rank 1 separately. But here, because the data set was given in that way, automatically we fit the data set as conductors, fixed interval. But that was actually crucial. And then literally we take the average. So n is just prime count from the 0, first prime to whatever the n may grow, but the second prime, etc. So n is the prime count, and conductor range is from n1 to n2. R is the rank, and then this is simply the average. Then we plot the rank 0 case in blue, rank 1 case in red.
Quick question, and just a little turnaround. When you say a set, is it some set that you choose from some data distribution, or is there some canonical set?
Here all the elliptic curves in this range.
Okay, so they're all known. It's all
known, all known.
So it's the set in that range.
It's the set. Thank you. And then Alexei did this and then showed me this picture. And then this was amazing. Why is this amazing? The first behavior was not a surprise because we knew that APs tend to be smaller when the rank is bigger on average. So here you should go, rank 1 go down, rank 0 go up. That we knew. But no one expected the averages to switch positions No one actually expected the red dots go up and then blue dots go down. And then moreover, this oscillation came to a complete surprise. The oscillation was really, really surprising. Then, of course, we showed this picture to many, not that many, so several experts first. And all of them were very surprised. And they didn't have immediate explanation. So we knew that this is new. We came to know that this is new.
So the first plot was the weights of PCA1, the previous one, and this is average AP. So is PCA1 just the average of the APs?
No.
Why is there a similarity between the two?
Because here, the PC1 tries to distinguish blue dots from red dots. Okay, and then the PC1, the coordinates, shows you how primes are important. But here, because there is no separation, the primes around here is not very important. But here, it is completely separated. That means the primes around here are very important. So that's why in the coordinates of a principal direction, we are seeing some oscillation. Okay, they are correlated, but not exactly the same.
It's not PCA, right? It's linear regression coefficients, right? It's just logistic regression coefficients.
It was PC1, but linear regression coefficients may show similar thing. The plot I showed you was from the
But
PC1.
it's PCA for just rank 0, say. 0
and 0, 1. I mean the set consisting of a rank 0 and rank 1.
Okay, so you're taking the fact that it's.
Exactly. Okay, good questions. And then we did for rank 0 and rank 2, and this was the picture. We could see that the parity of the rank is important. That rank 0 and rank 2 seems to have similar parents, even though their locations are different, because higher rank should go below. So that is comparable. I mean, this picture is comparable with that known fact, but oscillation pattern seems to be similar. And so we showed these pictures to experts. Among them, Drew Sutherland. Of course, we sent him these pictures, and then he asked this question: how does this oscillation change as the conductor range changes? Because we fixed the conductor range and produced the picture, and if we choose a different conductor range, we had a similar picture, but we didn't investigate it systematically. But he asked this question, and then he considered to explore or to answer this question. He considered this geometric interval from 2 to n to 2 to the n plus 1, and moves, so that it is a geometric interval. And because now we know that the parity is important, we can collect even rank K elliptic curves and see the elliptic curves of odd rank. Then we take the averages. And through plot these functions, even in the blue and odd in red. Then N1 from 13 to 17. And the pictures he obtained are these. Because the geometric intervals are disjoint, so these are all from different data sets. Okay, there's no overlap at all. So all different data sets, and here x-axis are scaled by 2 accordingly, because conductor ranges are scaled by 2, and except that trivial scaling, all the patterns are the same. The patterns are all the same. And here it's more solid because we have more points. Other than And clearly, this was not an accidental thing. Something canonical or something essential, something really important is on here. It showed that this phenomenon is a scale invariant. And the next question is, the question was, does murmuration occur only for elliptic curves? Because this question is natural, because we remember the modularity theorem. The theorem says an elliptic curve is over Q is corresponding to weight to modular form. So basically, we are seeing weight to modular forms, certain family of weight to modular forms in that picture. But we know that there are modular forms of other weights, 4, 6, etc. Then there are also higher genus curves. Elliptic curves are genus 1 curves. So there are higher genus curves. What if we consider these things? Our murmuration, is murmuration phenomena existing. Yeah. That was the question. Question was, will murmuration appear for these objects? That was the question. And the answer was yes. And then Drew Sutherland did an extensive computation. And then he maintains a web page for murmurations. So you can go to this web page. So I wanted to click, but it may bring some technical difficulties. So I made a screenshot. You see the screenshot of Drew Sutherland's page, but it's only like less than half. There is another half. And then he considered many cases, memory modular forms, weight 2, 4, 6, etc., and then all modular forms and the genus 2 curves, etc. So this is less than half. Then if you click one of these, then you'll see it will be magnified, and then you'll see an image how the murmuration changes. If you're interested, then go to the website and then see nice pictures. Clearly, murmuration was not only for elliptic curves, it is for other objects. There was something important. So this new discovery, the news of this discovery spread out. And there was a hot topics workshop at ISOM last year. People, experts, gathered, and then they discussed this phenomenon. And in less than 2 weeks, there will be a workshop at the Simon Center on murmurations. 10 days or 12 days, there will be another workshop. And the story about this discovery was featured. It was featured in Quantum magazine. Yeah, so basically, a lot of people got interested. Then they studied murmurations. And people wanted to have some rigorous explanations. So Peter Sarnock at Princeton and IAS, he wrote notes on murmurations. Then his student, Nina Subulina, proved the case of modular forms. Yeah, she proved murmuration phenomenon, and then she derived the formula for the murmuration function. And then there have been about 10 papers in just about a year on murmurations. Then the research on murmuration is still going on, and Yeah, that's the status. And clearly, this example of a murmuration demonstrates how machine learning experiments can lead to new discovery and the discovery of new structures in mathematics, particularly in number theory.
So to be clear, the murmurations phenomenon for elliptic curves is still open.
Yes, it is still open. So that's right. Nina, she considered all the ellipticals, all the modular forms coming from any coefficients.
And also varying the weight of the modular forms.
Yeah, I think she considered all the even weights.
Yeah, okay. So the elliptic curve case would be the weight, like k equals 2.
Yeah, and then coefficients are from Q.
Yeah.
That case is open. Okay, so this was a success, I would say. But in the remaining time, I want to show you another example in representation theory and algebraic combinatorics. It will be about the Kronecker coefficients. So I'll try to apply the same paradigm, and I'll try to show you how machine learning experiments can help us to find the new structures. So Kronecker coefficients. So it's collaboration with Georgi Gutbaya and then Fabian Goya. So unlike the murmuration, there was no canonical picture associated with the Kronecker coefficients. So, but I wanted to have a picture. So I asked ChatGPT to create a picture related to Kronecker coefficients. Then this was the picture. Do you see some Kronecker coefficients?
It seems appropriate somehow.
Yeah, I like it. So then, I have not defined the Kronecker coefficient yet. So what is the Kronecker coefficient? The Kronecker coefficient describes the decomposition of a tensor product representation of a symmetric group into irreducible components. So fixed notations make it precise. So let Sn be the symmetric group of degree n. And we know that the irreducible representations of the symmetric group over C are parameterized by partitions lambda. And here S lambda is the notation, it's irreducible representation. P of n is a set of partitions. Okay, so then let us consider this tensor product. Lambda and mu are partitions. Then this is still finite dimensional representation, and it is decomposed into irreducible representations. Then as nu varies, we get these decomposition multiplicities. Then these decomposition multiplicities, G, lambda, mu, nu, are called Kronecker coefficients. So of course, the symmetric groups are basic, very basic, and then irreducible representations are like, also like elementary objects in representation theory, and tensor product is a natural operation. So everything is like a basic and standard. So clearly, these Kronecker coefficients are fundamental structural constants, but they are very difficult to compute. If we consider this problem in the context of algebraic, actually like combinatorial representation theory and algebraic combinatorics, then this question is natural. Can you give a combinatorial description of the Kronecker coefficients? And we have a success with the Littlewood-Richardson coefficients for the tensor product of irreducible representations of general linear groups. We have a complete combinatorial description. So we want to have a similar thing here, and then this is a natural question. combinatorial representation theory. But it has been an open question since 1938. So, yeah, so there has been no combinatorial description of Kronecker coefficients. Of course, there are some special cases. The general case is no results.
Is there a precise definition of combinatorial description, or is that subject to interpretation?
That's a good question. So those people who study the complexity seem to have some definition, like a sharp P. I don't know.
Okay, so it's a complexity class.
Yeah. Like it is equivalent to counting something. Yeah, but the complexity of Kronecker coefficients seems to be questioned in that sense. I don't know exactly, but anyway, there may be some rigorous definition. But anyway, so it's open. And deciding whether a given coefficient, Kronecker coefficient, is non-zero is NP-hard. It is proven. So obviously, this calculating, just deciding the Kronecker coefficient is non-zero is already very difficult. But the situation is in some sense similar to the rank of an elliptic curve, because there the quantity is very important. Computation is difficult. Here, basically similar. These are fundamental constants. Somehow we are having trouble in computing this. So the natural question: can we use machine learning to determine whether a Kronecker coefficient is non-zero or not? Okay, we can ask this question. So how can we set up a machine learning problem for this? Then, of course, the input should be, in this case, the triple of partitions. There may be other things. But anyway, so that's the natural input data. So let Pn be the set of partitions. Consider lambda as an n-dimensional vector. So if n is equal to 6, consider partition 5,1 as 5,1, 0, 0, 0, 0. Then it is a 6-dimensional vector. So then the triple of partitions is a 3n-dimensional vector. So we'll use this as a data point. So now for each n, we have a machine learning problem. So the setup is not difficult in this case. So we have 3 n-dimensional vectors coming from the partition, triple of partitions. And then the target is 0 or 1. 0 represents the case when Kronecker coefficient is 0, and 1 means it is non-zero. Okay. Then this is a binary classification problem. When n is 14, we have a data set of 42-dimensional vectors. Okay, that's good for machine learning. And then the number of data points is about 2.46 million. So again, it's a reasonable machine learning problem. It is a binary classification. So I applied various machine learning tools, and then the result, again, was very successful. So the result was the accuracy was about 98%. Yeah, well, I was surprised. Here is more details. So I applied the nearest neighbors, convolutional neural networks, light GBM. Light GBM performed the best. But the point is, we observed high accuracy. So machine learning algorithms are seeing some patterns clearly.
Is the data set balanced in terms of?
Yeah, here. The data is just slightly skewed, but we may choose
It's pretty balanced.
yeah, pretty balanced.
Okay, good.
So it has no problem of choosing this many data points equally. Good question. So again, this is a very reasonable machine learning problem. Okay. I changed some input formats, and the accuracy varies slightly, but in any case, doesn't change much. And the point is, we got high accuracy. And of course, I wanted to see what's going on. I did some analysis, PCA, and then I looked at the coordinates of the principal directions, and I considered the various embeddings of the data set, and all these efforts made me introduce new concepts in the study of Kronecker coefficients. So I will define these new concepts, but the PCA plots and all these are not very pretty, so I didn't bring the pictures. But anyway, the results of these analysis is results in like a new concept in the study of Kronecker coefficients. So here, okay, the point is we are taking a data scientific approach instead of an algebraic or a combinatorial approach. So traditionally, people have been trying to apply algebraic or combinatorial method, but here we are departing from the traditional method, and we are taking a data scientific approach. That's the difference, and I think that's new. And this approach naturally gave us these new concepts and definitions. So, in some sense, the following definitions are main results. Let's see. First, we consider similitude matrix. What is it? So let us write the size of a set of partitions as P of n, little p of n, and consider matrix P sub n. Each row represents a partition of n. So basically, I will show you the example immediately, but we have a collection of partitions, and then in some sense, this is our data set, data matrix, and consider this matrix, Yn. Then, as you may recognize, this is a slight variation of the covariance matrix, because here we didn't normalize using the mean and the standard deviation, but it's basically close to the covariance matrix. Then we call Yn the similitude matrix. And because this is a covariance matrix, the largest eigenvalue and the corresponding eigenvector is roughly related to the first principal direction. So that motivates the next definition, but before that, let us see the examples. So this is P6, and 6000000 is the first partition, and then 1111111 is the last partition, and these are lexicographically ordered. And we keep the lexicographical order all the time. And this is a similitude matrix. Okay, and then now definition of A loadings. Again, this is motivated by the definition of principal direction. So let V be an eigenvector of the largest eigenvalue of Yn. And we may take an eigenvector that all the coordinates be positive as possible. And we denote by Vmax the largest coordinate and V mean the smallest coordinate, and make some normalization. This is just normalization because usually the numbers are not very pretty or the ranges are not very good. So just normalization. So V max will become 100, V min will become 0. This normalization. And the value A lambda is called the A loading of a partition. And here is an example. If n is 6, the A loadings are given by this. And 6, comma 0, 0, 0, 0, 0 has A loading 100, and 1, 1, 1, 1, 1, 1 has A loading 0. And then n is small, 6 is small, so it's constantly decreasing. So, but it's not the case in general. So A loading is not completely comparable with lexicographic theory. And it measures, in some sense, the similitude matrix measures how two partitions are close to each other. So we may consider the opposite. Opposite is the difference matrix. So we define this matrix as Zn. The lambda mu coordinate of this matrix is the sum of the differences of the parts. So lambda has these parts, mu has these parts, take the difference and take the sum. So then it measures how two partitions are different from each other. This is obviously a symmetric matrix. Let's call this matrix the difference matrix of several partitions. Here is an example. On the diagonal, you have all zeros because two partitions persist. One partition is not different from itself, but here you have a big number because the corresponding partitions are far from each other. And then we apply the same idea of the principal direction. So we define B loadings. So it's parallel to the case of A loadings. So we consider an eigenvector of the largest eigenvalue. We can take all the coordinates to be positive. It's the result of a Perron-Frobenius theorem. And then we find out the largest coordinate and smallest coordinate and do the normalization so that the largest one has 100 and the smallest one has 0. Then let's call the value B lambda B loading of this lambda. Then this is an example when n is 6, B loadings are given by these numbers. So now 6, comma 0, 0, 0, 0, 0 has a 100, 1, 1, 1, 1, 1, 1 has a 100. Right? And where is the smallest one? In the middle. And the partition is 3, 2, 1, 0, 0, 0. And if you know the notion of conjugate, 3 to 1 is a self-conjugate. And these two are conjugate to each other. So it's different from A loadings. But we defined all these to apply this concept to the study of Kronecker coefficients. So we have to consider the triples. So for the triple of partitions, lambda mu nu, we write just a G of t instead of G lambda mu nu for simplicity. And then define the A loading of T by this. It's basically the sum of A loadings of individual partitions. It's a simple and natural definition. And B loading is this sum of B loadings of individual partitions. And we are interested in the distribution of these loadings because it may be directly related to some, the question we are asking. So let us see the distributions. In histograms of A loadings, RDs for n equal to 15 and 16 case, or I mean, if n is getting bigger, then you get the same picture. And clearly, they show normal distribution. It seems that they follow normal distributions. And actually, I did a curve fitting, and curve fitting is almost perfect. You may conjecture that actually distribution of A loadings is normal. What about B loadings? I got these pictures, and the curve is coming from the gamma distribution. Then the curve fitting is almost perfect. So we may conjecture that the distribution of B loadings is following gamma distribution. And if we sketch the histograms now according to the information whether Kronecker coefficient is 0 or non-zero, that's directly related to our original question. And for A loadings, so the normal distribution case, we have this picture. And the shapes are different. So red region is corresponding to G of t is non-zero, and then blue is corresponding to case G of t is 0. The distributions are different, but no real separation. I mean, if you just click CD x-axis and no separation, there is some separation, but not much. What about B loadings? The pictures are these. And this is good. This is good because there is a peak. So if we find out this point, then below this point, everything is non-zero. I mean, the Kronecker coefficient is non-zero. So if you know this point, then we may say, we may conclude that all the partitions here, triples of partitions here, have Kronecker coefficient non-zero Kronecker coefficient. And actually, the red region seems to be following gamma distribution itself. But in any case, this lower bound will be very important information. So I define B star in the lower bound. It's the minimum of B of t, where G of t is 0. So like the edge of blue region. So if we know that value B star, then whenever B loading of the triple is smaller than B star, we can immediately conclude that G of t is larger. So for example, when n is 18, let us consider this triple of partitions. Can you determine whether the Kronecker coefficient is 0 or non-zero? By hand, you may take probably it's not a good idea to calculate it by hands. But B loadings, of course, the B loadings also should be calculated by computer. I mean, there is a good algorithm, power iteration. So finding out an eigenvector of the largest eigenvalue can be done very efficiently. So that's not a problem. Finding out this B loading is not a problem. It can be done very efficiently using power iteration. And the B loading of this triple is 41,07. And what's the value of B star? Of course, I could not calculate it theoretically, but empirically, it's around 44.818. And it is smaller than B star. So we immediately conclude that the Kronecker coefficient is non-zero. So how?
That's a conjecture, right? That statement in the box is a conjecture?
Oh, no, it's the consequence of the definition. So here, the non-trivial thing is this. All the others are trivial.
But there's to prove, I mean, is the claim that GFT must be zero, or the claim is that it's likely to?
It is zero. It is zero because I mean, if this is correct,
Say,
yeah. But I investigated as much as I can, so I believe it's true empirically. And then and the other things are following from definitions.
So the non-zero side is definite, zero side would be probably still.
Yeah, right. So if you look at this again, so this is the distribution. This is the zero side. Here, red goes all the way up to here, and then it's the number of these are number of triples of partitions. It's very small. So even if we know something about the value, it's not helpful. But this is different. As soon as we know the value here, this chunk will have a non-zero.
Maybe I'll say for a question, because I was thinking of a similar criteria, but it would be a little bit around.
Yeah, okay, yeah. So,
You have 5 more minutes, so.
yeah, right. So, yeah, we are okay. I'm almost done. So, yeah, that's right. So once we know the value, then this is automatic. Then how efficient it can be when n is 20, the number of triples is 246 million. The number is big, and among them, 78 million triples, more than 78 millions, satisfy this. So for these triples of partitions, we can immediately say the Kronecker coefficient is non-zero. That's about 31% of all triples of partitions. Okay.
So in a sense, I mean, the problem is NP hard, so you kind of hope to solve this. So when we're looking for
Worst case, of course, would be.
exactly. So when you're looking for a very strong sufficient conditions, so sufficient conditions to apply to a large number.
Yeah, of course, it could be even like 99% of the examples you could solve it.
Exactly, this case is 31.8, but yeah, so we are trying to find the strongest.
Yeah, for the remaining, if we flip the point, then probability becomes about 65%. Anyway, so for this, yeah, we can get 100% an answer with 100% confidence. Then during this program, I worked with Yogi and Fabian. So it's too early to report anything concrete, but we applied Kolmogorov Arnold network, COM. It's developed by Fabian and Jim. And also we apply the symbolic regression and small neural networks. The goal was to see some explicit formula or some very clear interpretations. And the initial results we obtained so far are very promising. We study further and get some report or paper soon. And the good thing is, it seems that all these models seem to become stable when n is becoming getting bigger. That's the thing. As a concluding remark, so I try to show you that machine learning can help us discover new structures in mathematics. Mathematics title. And however, for now, it remains crucial for human mathematicians to be actively involved, offering insights and perspectives. So all these examples, human intervention was crucial. Okay, that's all for today. Thank you.